Okay. Okay. So when we left off last time, we were talking about the action potential. So we've covered our general resting membrane potential and how it gets set up. We talked a bit about graded potentials and this idea of having to get to a threshold potential before we kick off our full action potential. And then last time we spent a fair bit of time focusing in on our different voltage gated channels and how their response to that threshold membrane potential, so that change to the membrane potential, is what kicks off our action potential, which is going to be sending a signal down our neuron to our next neuron in line or to a target tissue. So you should have a picture like this in your notes, and we walked through it last time, and these next two little questions are going to be referring to this. So I want you to notice that along this time, we have a couple of time points marked out for ourselves. So A here at the beginning, B here, C here, D here, E, and then F. And what we're going to be doing as we understand the progression of an action potential and how it works is we're going to be trying to understand what's happening at these different points in time. We're going to give it a go on our own at this point first, and then we're going to focus in on some of this stuff in detail in some of the text on our next several slides. So we're going to start out. Okay. We're going to have different phases of our action potential, and we're going to have a depolarization phase. So we're going to predict which ion is going to be responsible for that. Then we're going to have a repolarization phase. We should be able to guess or remember which ion is going to be responsible for that repolarization. Talked about what depolarization and repolarization mean in terms of directions of change for the membrane potential. And we've been previewing how those are going to relate to our full phases of the action potential. Okay, great. Yeah. So depolarization means that we have our membrane potential going up from rest. So that's going in a more positive direction. That's because of sodium. We know that sodium's equilibrium potential is positive 60, it's super high. We know sodium wants to come into cells. Now we know the how, right? We know we have a voltage gated channel for sodium. So when sodium comes in, this depolarizes our neuron, leading to this spike that results in the action potential. And what goes up must come down, so that's repolarization is coming back down. We know potassium has an equilibrium potential of about -94, so even below our resting membrane potential. So when we open our voltage-gated potassium channels, our next piece, we repolarize, we come back down. When we think about our neurons, those are always the directions we're thinking of for our ions. Sodium's always going to want to go in, potassium's always going to want to go out when we're thinking about our neurons. Okay. So looking at our diagram with those time points, oh, can we see all of these on class? Okay. I want you to find time points B and C. And I want you to check off which of these things are true. So that's the last one. Okay, so we actually can. Okay, so several of these are going to be true between time points B and C. It's only letting you pick one. Yeah. Okay, pick your favorite then, guys. Okay, great. Okay, so we'll take a look back at the graph in a second, but all the green ones are going to be correct. Okay, so what we're looking at. Okay, so we were looking between time points B and C. Right, so from B and C, we're looking at basically from right about the time we hit this threshold membrane potential, right, to C, the time when we spike up to +30. Right, so the red line is our membrane potential, so the actual change on charge in the cell. These two blue lines of different hues are our permeability to sodium and then our permeability to potassium. So how much sodium is able to move versus how much potassium is able to move. Okay, so as we're thinking about that time period, right, first bit, we can see that the membrane potential is going up, right? So that's the depolarization bit, right? So between B and C, we're going from threshold up to +30. We're going up because sodium is moving. So sodium is moving into the cell. That's what's causing this depolarization. Sodium is able to move into the cell because our voltage-gated sodium channels are open. So we talked about the two gates on the voltage-gated sodium channel last time. Talked about that activation gate. And so that activation gate has activated, it has opened once we hit threshold. So that activation gate is open, and our inactivation gate is still also open. There's a little bit of a time delay before that second door swings closed. So those voltage-gated sodium channels are open, which is why sodium can move into the cell. And another way of describing the fact that sodium can get into the cell through this open voltage-gated sodium channel is to say that our sodium permeability has increased or is increasing. Right? We've got more doors in the membrane through which the sodium can flow. So that's what's happening during this first phase of depolarization in our action potential. So these next couple pictures are the same, but just drawn differently. Right? We're still just looking at the same thing. We're still just trying to come up with as many ways as we can describe or understand why and how we see this spike to +30, right, of our membrane potential is what the action potential is this spike up to +30. happening with several distinct phases that we can describe. So we can see that when we get to our threshold, right, this is when we had our voltage gated sodium channels opening and sodium coming in, right? So that's causing this rise in the membrane potential. And we can see down here, what this chart is looking at is our sodium and potassium diffusion. So how sodium and potassium are moving through channels. And so basically this is the permeability stuff just pulled out from that combo picture we had before, right? So we can see here that our sodium channels opened, right? We have sodium moving in, right? About the same time as we hit this positive 50, then we can see that the inactivation happens later and is what starts off this big drop later. Okay. So we mentioned last time, same thing, that this is a positive feedback loop when we think about the action of the voltage gated sodium channels, because one sodium channel opening has a tendency to raise any neighboring patches of membrane to that threshold as well, right? Because it depolarizes them all a little bit. So we have one voltage gated sodium channel open, and then another, then another, then another, then another. That's positive feedback. Okay. So this shoots us up way over zero, gets all the way up to positive 30. So this whole going up phase is our depolarization phase of the action potential. But it stops before we get all the way to the equilibrium potential for sodium, stops before we get to positive 60, stops at positive 30, because we have these inactivation gates on our sodium channels. And we see those inactivation gates swing and close kind of on the bottom of the voltage gated sodium channel, ultimately blocking the movement of sodium into our cell. All right. So at that time point when we're hitting 30 millivolts, that's when our inactivation gates for sodium are closing. And this is the same time at which we see our voltage gated potassium channels opening. Right, so both that inactivation gate on the sodium channel and the potassium voltage gated channel, the whole thing, are on a little bit of a time delay when we think about the response to reaching that threshold voltage. So we stop seeing sodium coming into the cell because those voltage gated sodium channels are closing, their activation gate, their inactivation gate is closing, right? And we see the potassium channels opening. The reason that that's important is right, like if we just closed the inactivation gate on the sodium channels, we'd probably just end up kind of plateauing here at positive 30, right? If no more sodium is coming in, that wouldn't necessarily fully drop us down, right? It would just stop this from continuing up, right? So what we've done is we've blocked sodium from coming in, which means we're not going up anymore. And then the potassium channels opening cause the potassium to leave, which is what pulls this line into actually going down. So there's a subtle difference between what's going on with the sodium and the potassium here. So they're working together in order to have this overall effect. So this part is basically a negative feedback loop because we've seen a spike to positive 30, and now we're coming back down towards our original state, towards rest. All right. So here's a table of some things that you may want to know as we're thinking about our action potentials and their different phases. So what we're looking at for our resting membrane potential versus our depolarization phase. So that's like phase one. Repolarization phase can be part two of our action potential. And then our after hyperpolarization is going to be a slight overshoot of the resting membrane potential. So like part three of this action potential series. Okay. So in each of those time points, we can say, what's our membrane potential? So what is the actual state across the cell membrane? If we measure the inside of the cell and the outside of the cell, what would the difference in charge be? So we can see that we have this change from -70 at rest all the way up to positive 30 during the depolarization phase, back down to negative 70 for repolarization. And then, oops, we overshoot with our potassium continuing to rush out of the cell down to about negative 85 before our sodium potassium pump eventually brings us back to our normal resting state. Okay. So we're going to want to know what our membrane potential is, like what the actual charges are for each of these phases. We're also going to want to know about our channels and our ions, right? So we're going to want to know about our voltage-gated sodium channel. Right, we're going to want to know both, is it closed or open overall? Like, can sodium get through? Right. And we're also going to want to know why, because it has these two gates. So the voltage-gated sodium channel, a little more complicated than the potassium one. Right, so we can see here that at rest, our activation gate is closed, but our inactivation gate is open. Right, so here's the problem. Here's why sodium is not flowing through this channel right now. It's overall closed because that activation gate is closed. Then during depolarization, we've triggered that activation gate to open. Nothing has happened to the inactivation gate yet, so they're both open, so the whole channel is open. So this is why we see lots of flow of sodium into the neuron. Then during repolarization, as we're coming back down, we can see that the activation gate actually hasn't closed yet, right? But what's happened is that we have our inactivation gate closing, right? So this is why overall, the entire voltage-gated sodium channel from the perspective of the sodium ion is going to be closed, meaning we don't have much sodium coming into the cell anymore. And then eventually we're going to reset back to that original resting state. So we can see that eventually the activation gate closes up and that inactivation gate swings back open. But it doesn't really matter because overall sodium can't get through until we do this whole thing. So you're going to want to be able to do that kind of thing and think about these things precisely as we're understanding our action potentials. You can abbreviate this table if you're studying, but this is a font of potential questions, right? Using this table, you can get to any kind of question about what's the membrane potential during this phase? What's going on with the gates? What's going on with the flow of sodium or potassium? So I recommend, if you like practicing things in fill out a blank table form, this is a good one, which is why I pulled it out for you. Okay, so that's table 7.3 in your books. So back to thinking about the action potential and kind of what it's for. Okay? So when we have a cell where we have the ability to have this change to the membrane potential for communication or for a response, we refer to it as an excitable membrane, right? So it's responding to these changes in ion concentrations, which are resulting in changes in voltage. Okay. So when we have an excitable cell, it's going to have the ability to create these action potentials, to create these large spikes in charge. So we mentioned our graded potentials before as being for kind of small scale communication, right? So we could have small membrane potential changes affecting one part of the cell and spreading out the decaying towards other parts of the cell, right? So we can have kind of within cell communication in that way. But our action potential, its point is large scale communication through the whole cell, because our end goal is going to be to communicate with some other cell at the end of the neuron. So we want to remember like what our neurons kind of look like, right? So we had our soma, the cell body, right? We had dendrites, so kind of processes that might be receiving signals, right? Then we had an axon hillock, so kind of pinching off before we lead into the axon, which is a long, skinny structure that then leads us to our axon terminals. I'll just draw one this time. The kind of button that's going to be talking to our next cell, which might be another neuron, right? So something like that. Not every neuron looks identical to this. There are many different types of neurons, but these are the basic types of structures you'd see in neurons. So for our purposes, this is what neurons are going to look like. Okay. So our action potentials are going to be traveling down from the axon hillock, which is here, down the axon to reach our axon terminal, which is where they're going to start talking to the next cell. Right. So again, we're going to run through this stuff one more time. This is still just the same description of how an action potential works. Right now, we're just focusing in on that permeability state. Right, so across this action potential, right, at rest, so starting out, we saw that our permeability to sodium was lower than our permeability to potassium, right? So we know that at rest, we have lots more potassium able to flow than sodium. They're labeled over there, but I'll label them at the beginning as well. Okay. Right. And this is why our membrane potential for our resting membrane potential is closer to where potassium wants it to be. So closer to that equilibrium potential to potassium, far from sodium's equilibrium potential. Okay. Then as we depolarize, we see that there's a little bit of a change, right? So not a ton is happening in terms of changes to this potassium permeability. So potassium is mostly going to behave the same, but as we depolarize, right, part of why that action potential is going, or part of why the gradient potential is leading us to threshold is we have positive charges coming into the cell. Well, that probably means sodium, almost always, right? So sodium starting to be able to come into the cell in reaction to some kind of stimulus. And this is our gradient potential, bringing us to the threshold. Okay. Then at threshold, this is a trigger for our specific actions, right? So reaching threshold triggers our voltage gated sodium channels to open. This happens over and over again. It's regenerative. Okay. Slowly, those sodium channels start to close as the inactivation gate starts to swing closed over time. And slowly over time, our potassium voltage gated channels are opening, getting us to flatline at positive 30 and drop down respectively. Okay. So this is why we don't get up to positive 60. It's why we get stuck at positive 30 and then drop back. So here's the repolarization and then the after hyperpolarization bit. So that was what was on that table, that after polarization. Okay. So here we can see that the action potential is coming down, right? This membrane potential is dropping because we have our closing sodium channels and our opening, right? Potassium channels, they're opening. Okay. So we're going to call it repolarization till we get to negative 70 because that was our resting state. And then the after hyperpolarization is the fact that we're overshooting, right? So this extra negative bit. Okay. This is because those voltage gated potassium channels stay open a little extra long. Right, so that permeability, that extra permeability to potassium lasts a little bit longer than it actually took us to get back to the resting membrane potential. So we get even closer to our equilibrium potential for potassium than we were when we started off. Okay. Finally, we eventually do get back up to negative 70. So this is through the action of the sodium potassium pump, which we know is pushing 3 sodium out of the cell, pulling 2 potassium into the cell. As it does this enough, it eventually balances out our concentrations again, like they were to begin with, setting us back to the resting membrane potential. So this is how we're like resetting the neuron so that we can potentially do this again. Right? This would kind of suck if every nerve could fire just once and then we're done. Right? That would not be compatible with life. So here's a picture that you might use to focus in just on what the charge is on the cell, so just on the membrane potential, dividing out our different phases. right? So here, our phase one would be that depolarization. Here, our phase two is that repolarization. And here on the slide, we have described that phase three, that after hyperpolarization. Okay. All right, so that's about that overshoot, making sure that we have that explanation strictly down in our notes. That this is getting all the way down to -85, that we're not getting all the way to potassium equilibrium potential, because eventually those potassium channels are getting inactivated and we have a sodium potassium pump reestablishing our resting conditions. So you've got like 3 or 4 different sets of images, all of which are saying the same thing. So you want to be able to practice for yourselves later on. Can I draw an action potential, right? So can I draw the change to the membrane potential? Can I draw how it spikes up? Can I draw how it spikes down? Can I label for myself depolarization, repolarization, after hyperpolarization? And then you want to be able to link that up to understanding what's happening with sodium and the sodium channels, what's happening with potassium and the potassium channels during each of those phases. You've got options for which picture makes sense to you. They are all correct. They are all actually the same. Okay. All right. So if you were looking in a physiology lab, you might see action potentials looking a little blurrier. The way you read them, right? You're gonna just notice them as spikes, right? You might not even be labeling the spikes. Right, so these are our 3 action potentials here in this image, are these 3 spikes. Right? So they all would have those same phrases we've just described, that initial graded potential, rise to threshold, depolarization phase, repolarization phase, potentially after polarization phase. We'll talk about why that's a little squidgier. So this is what you would look like. And you might be linking it up to stimuli, right? So your stimuli might be shocks, right? So actually it's sending a little bit of an electric shock, trying to get some type of excitable tissue to react. All right, so when we see physiology diagrams like that, those are often like little arrows on the bottom, are often stimuli. Okay. So what we want to know about action potentials as an important way that they differ from graded potentials is that all of our action potentials are the same, right? Like we either spike up to +30 or we don't. We don't have like half an action potential ever, right? We either have an action potential triggered or not. That's different than our graded potential. So we can have bigger or smaller, weaker or stronger graded potentials, but not action potentials. Action potential is this specific thing, this specific spike to +30, which is why we can draw it a little lazy depending on what we're focusing on, because we know that an action potential is an action potential. Okay. So every time we get to the threshold, every time we get to -55 millivolts, we are going to fire an action potential. If we don't get to -55, even if we have a little bit of a change to our membrane potential, we would call that a sub-threshold depolarization. So sub for below, threshold for threshold. We didn't get to threshold, we are not firing off an action potential at all. A supra-threshold depolarization, so supra, more, extra, above, right? Even if you have a really strong stimulus, you're still going to just fire the same action potential. You're not going to have an action potential that like gets to +50 instead of +30 just because you had a really big stimulus. That's just not how they work. It's just always going to be an identical action potential in response to anything that hits that threshold. Okay. So we're going to have action potentials the same magnitude regardless of how big your stimulus is, so long as you hit that threshold. So when we think about how we change signals in the body, how we would tell a muscle that there's a really big stimulus. You're not going to do it by changing how tall, how high the amplitude of this action potential is. What you could do is pack action potentials closer together, right? So we're going to be thinking about like poking faster as telling your body that we're getting more of a signal instead of like poking harder. Okay. So once we reach the threshold, this is our all or none principle, our all or none law. Once we reach threshold, we will fire an action potential. Size of the stimulus has no effect on what that action potential looks like. It's always the same, always just spikes to positive 30. Doesn't affect even how long that action potential is happening. And by how long, I mean like how long it took us to get to positive 30, right? So like how wide this is doesn't change, right? So that part is also just always going to be the same, right? The only thing that eventually later on we'll add on as a caveat is how much space there might be between action potentials. Okay? But nothing about the action potential itself changes. So here we see linked up, again, some action potentials, graded potentials, and stimuli. Okay. So here we're looking, let's start with the bottom. We're looking at stimuli and we're looking at how strong they are. All right, so here we have two little stimuli, two subthreshold stimuli. We can see what they do. Create a change in the membrane potential. But these aren't action potentials. These are just little graded potentials, and they're ones that don't get us to threshold, so they fade away. So no signal is happening towards the other end of the cell. This doesn't fire off a big wave of charge down the axon. A threshold stimulus, so one that gets us just to negative 55, does fire off an action potential. Great. And a super threshold stimulus, so a super strong stimulus, that would be really big, still just fires the exact same action potential. Right? So this curve and this curve look the same, even though the stimuli were of different strengths. Right? Didn't have an effect on what our action potential is. So that's our all or none law of action potentials. So here's another way that we can practice checking whether we understand action potentials. And this is about giving you potentially too many resources and too many ways of thinking about it, right? So at the top of this, looks like it's cut off on the screen, but it says threshold stimulus at the top, right? So what we're thinking about, so we have a stimulus creating a depolarization of our membrane, right? So we know that this is going to eventually cause a spike up to positive 30 as sodium comes into the cell. And then eventually we're going to fall back down to rest and even below as potassium starts to leave. So we can see why that's happening in that order. First sodium coming in and then potassium leaving. Because we can see our first effects of that depolarization of the membrane to threshold is we increase the number of open sodium channels, which increases our permeability to sodium, increases how much sodium flows into the cell, and then we have our delayed effects kick in about a millisecond later. So the delayed effects affect both sodium and potassium. So they're both actually ultimately still responses to that depolarization to threshold. They just take a little time to kick in. So for sodium, we're closing that inactivation gate, meaning that we see a drop in membrane sodium permeability and a drop of sodium flowing into the cell. And on the potassium side, we're opening our potassium channels, increasing how many of them are open. So increasing our membrane permeability to potassium, increasing how much potassium is flowing, and it's going out. So together, that stopping of sodium coming into the cell and that increase in how much potassium is escaping gives us our drop in charge on the cell. So that's what defines our repolarization. So if you don't like studying in table format, this has all that same information as that table did, right? It's got information about permeability, got information about our charge, and it's got information about our channels and the gates. But here's that chart again. So a reminder, we do want to make sure that we can tell the difference between our action potentials and our graded potentials, which we talked about last week. Right, so they differ in where we see them, right? So the location, our graded potentials are happening in dendrites, which receive signals, and in the cell body. Our action potential is starting in the axon hillock and then really propagating throughout the axon. Our graded potentials are weak. They vary in how big they are. Not true for our action potentials. We're going to see that the direction of change in the membrane potential, because we saw this, can go either direction. So a graded potential could bring the membrane potential up, could bring it down. Our action potential always depolarizes first, always goes up first before we reset. Graded potentials can be added together. Action potentials can't. An action potential is just an action potential. We'll talk soon about our refractory periods. We've already talked a little bit about channel types. So voltage gated channels are our big thing for action potentials. Graded potentials are going to be for ligand gated channels. So responding to stimuli when like different molecules and neurotransmitters attach to this other type of channel. Ions we're interested in for our action potentials is sodium and potassium. Graded potentials got some variability, still usually sodium and potassium, maybe some chloride. We've got some options. And the length of time is a little bit different. So we have a few milliseconds to seconds for our graded potentials, and specifically 1 to 2 milliseconds for our action potentials. Let's think about those refractory periods since we got a couple more minutes. Okay. So here's another picture of our action potential. So you can see it goes up. That's our depolarization phase. It comes down to -70, repolarization, and it overshoots a little. That's our after hyperpolarization. So when we think about sending increasing signal out to the body, say you want a gland to make a lot of a specific type of enzyme, right? We can't send a bigger action potential. That's our all or none law, but we could tell it, do it again, 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 right? We could pack action potentials close together, but there's only so close we can pack them, right? There's only so fast we can send a second action potential down our axon. And that's what our refractory period is about. Our refractory period is what's putting a barrier on how close together you can pack action potentials. Okay, so we're going to have two types of refractory periods, and we're going to specify which one we're talking about. So here we see in this kind of peach color, this is our absolute refractory period. So this is where we would be in our absolute refractory period, meaning you absolutely cannot send off another action potential during this part of time. Right? During this chunk of time, there is absolutely no way you could fire off another action potential. That's not the case for our relative refractory period. So our relative refractory period is here in blue. So you'll notice this relative refractory period happening from the time we repolarize and through this after hyperpolarization phase. So what our relative refractory period is, the time when it's really hard to fire off a second action potential, but you theoretically could do it. It'd be more difficult than firing the first one was, but it's not impossible to stack another action potential that close. next to our first one. Okay. So our relative refractory period named because it's relatively difficult, but not impossible to fire a new action potential during this chunk of time. Okay. So these two phases are different. These two refractory periods are different because of what's making it difficult to fire off a second action potential, right? So when I say a second action potential, I just want to make sure we have an idea of what I mean. Right, what I mean is like, this is our initial action potential, right? We could fire potentially off a second action potential here, but we couldn't fire a second one off like here, right? So that's not possible. You can't put one in the absolute refractory period. You could maybe potentially fire off another one here in the relative. Okay. So what's going on here? So during the absolute refractory period, right, this is encompassing first our depolarization phase, right? So that phase one of the action potential, that depolarization phase one, depolarization. Okay. So we know that during this depolarization phase, the sodium channels are already opening, right? We wanted to fire off a second action potential. There's nothing more you can do. You're already opening the sodium channels, right? If you send another stimulus, those channels are already opening. We already have this domino effect going. There's no way to increase this effect during that depolarization phase. Now, the second part, the second phase within the absolute refractory period is our repolarization, right? Okay. So now we have our membrane potential coming back down. So we might initially think, okay, just send it back up again. But we can't do that because our sodium channels aren't just closed, they're inactive, right? So during this repolarization phase, we've just had those inactivation gates swing closed on the bottom of the voltage gated sodium channels. And those don't open back up with anything but time, basically. It takes some time to reset them. You can't send little electric zaps at them and make the inactivation gate open. The voltage only causes the activation gates to open, right? The way in which inactivation gates responded to voltage was with a time delay, and what they did in response to that time delay was to close up. There's no way you can make inactivation gates open up before they're ready. Right? So this is why we can't just turn back around and shoot up and up and up more during the second part of this absolute refractory phase. And the relative refractory period, this is during that third step, that after hyperpolarization, right? Okay. And what's happening here is that our voltage gated sodium channels kind of reset at this point, right? So we've gone back to an inactivation gate that is open and our activation gate is closed. We're dipping down low, right? We're not at rest because we have a bunch of potassium channels that are still open. So the voltage gated potassium channels haven't closed back up. They're not done with their response. This means that if you send in a stimulus or if you send in something that would usually cause a graded potential, instead of just fighting against this potassium that's leaving through leak channels, like it does everywhere and always, you'd also be fighting against the fact that extra potassium is coming out of these voltage gated channels. But if you have a really, really, really strong stimulus, it might be big enough to make up for it. Might be big enough to make up for that extra leak of potassium if you have a strong enough stimulus, in which case you could manage to hit threshold during this period. And if you hit threshold, you fire off an action. It's less likely You need a really strong stimulus, but you could do it. Regardless, if you did manage to fire off an action potential during that relative refractory period, it would look the same as any other action potential. It would still just spike up to positive 30 in these phases as our original one did. Okay. So to break that out, put another picture on it, right? This is just comparing it to how many of those channels are open, right? So this is showing us how many sodium channels are inactivated, how many voltage gated potassium channels are opening, right? I guess really these are our permeability lines. Yeah, anyway. So the absolute refractory period is spanning all of our depolarization phase as well as the repolarization phase, because we have these sodium gates first opening in the first place and then they're inactivated. The relative refractory period is because we have these voltage gated potassium channels still open. And some of those sodium channels have reset and are able to reopen. Not all of them, some of them are still inactive. This is going to take a little bit of time for all of them to reset, but enough of them have reset that it's potentially possible to fire off a second action. Okay. So we're going to stop there and we'll talk about propagation next time.